start this off with a basic algebra problem. So here we have a graph. A speed and time graph. Time is your x in hours and speed is on your y in miles per hour. And we have a constant 20 miles per hour indicated by the red. Let's look at the follow-up questions. Number 1, calculate the area under the curve in blue. What does this represent? Well, area is easy. Area is just base times height. Your base is 1. Your height is 20. So your area is 20. What does this represent? Well, let's look at units. So the units of our area, so for the base it's hours. For the height is miles per hour. Hours cancel out. You get a unit of miles. So this whole blue region represents 20 miles. It represents a quantity of distance. Number 2, sketch a graph of the distance time graph corresponding. So TD 0 to 1. Okay, so how do we find our points for our distance graph? We can use our fun little formula, distance equals rate times time. So for time equals 0, we're going to have a distance of 0 because 0 times anything is 0. Now let's look at 0.5. So at 0.5 hours on our speed time graph, you are still at 20 miles per hour. So 0.5 times 20 is 10. And at time equals 1, 1 times our rate at time equals 1 is 20 miles per hour still. So it's going to be 1 times 20, which is 20. So that's our graph. Number 3, find the slope of the distance line. Are there any connections between speed and distance? Slope equals d2 minus d1 over t2 minus t1. Our final distance is 20 miles minus 0. Our final time is 1 minus 0. So our slope of this line is 20. Are there any connections between speed and distance? Well, let's look at units. Miles, the d2 minus d1 is in miles. t2 minus t1 is time, which is in hours. And this is a measure of speed. So this 20 is actually 20 miles per hour, which is the same value which our speed and time graph is at. So we can say that the slope of our distance time graph is equal to our speed and time graph. So let's put this in calculus notation. The slope, or d over dt, the derivative of our distance function, I'm going to call f of t because there are a lot of d's, I don't want it to get too confusing, equals our speed function. So is there any way we can reverse this, put s of t in terms of f of t? Well, so how did we get our distance function to begin with? We found the area underneath the speed and time curve, and in calculus, we call the area under the curve an integral. This is the sign for an integral. Whenever you see it, always think of area under the curve. So let's break this down. We have the area under the curve of s of t, and we have specific indexes, a specific region of x, or a specific interval of x that we're evaluating this between. It was between t equals 0 and t equals 1. This equals f of t. So again, we've established that the integral is the inverse of our derivative. Okay, that's one thing. So we now know that this integral of s of t between 0 and 1 is a value. We actually found that value in the algebra section. We found that as 20, the area under the curve between t equals 0 and t equals 1. How can we put this in terms of the distance? Well, we can do final distance minus initial distance. 20 equals, our final distance is 20 minus our initial distance, which is 0. Another way we can write this is like this. We're using our lower and upper indexes as a way of finding this integral with the distance function. So, in a more broad rule, if I have a function f of x that is continuous, because let's see, this was continuous and this was also continuous, and that has an antiderivative called f of x, then we can say that the integral between any 2 points a and b of f of x dx equals to the antiderivative, or the integral, of capital F of b minus capital F of a. Those are the two main things to know.